Hydroboration is what's referred to as a diastereoselective reaction. Oh, that's a hard word to say. Anyways, what it means is there is a relationship between the H and the OH that's added. They are added syn to each other. That means they're added to the same face of the molecule. So if the OH is added on the top face, the hydrogen is added also from the top face. If the OH is added from the bottom face, the hydrogen is added from the bottom face. Now, in this case, the relationship of these two molecules are enantiomers. And so you can just pick one of them and write racemic. So this is the product that you get. What you do not get is the opposite diastereomer, where the hydrogen and the OH are on opposite faces of each other. Now, when you have a linear system, like so, you're adding hydroboration to this. Again, the H and the OH are added syn to each other. Now the OH goes on the less substituted side, the H goes on the more substituted side. That's part of the anti-Markovnikov selectivity. And so what you would do is if you draw the OH as a wedge up here, then the hydrogen has to be a wedge. Now if you draw the hydrogen as a wedge going up, then that methyl group is a dash. Or you could have drawn that hydrogen as a wedge going up here. In that case, this ethyl group is a dash. These molecules right here are the same. Now, if you drew your molecule, the OH, as a dash, then the hydrogen would be a dash. That would mean that methyl group would be a wedge. Or, if you had this OH as a dash, then that hydrogen would be a dash. Your ethyl group would be a wedge. Now these molecules right here are enantiomers of each other. So you just pick one of them. What you do not get is if this OH is a wedge, you do not get the hydrogen as a dash here. So if we look in terms of stereochemistry, this is an R chiral center. This is an R chiral center. You get RR. It's an enantiomer. It's SS. You get one of these two diastereomers. Sorry, one of these two enantiomers. What you do not get, though, is you do not get this one, or the RS. Or the enantiomer the SR. These are not formed in the reaction. So how to accurately predict them is you simply draw the molecule as it is with all the lines in the same shape, just like that. Add the OH as a wedge and add the hydrogen as a corresponding deal of the same face. Now, granted, you have free rotation about this molecule, this RR molecule. This is also RR. These molecules are the same molecule. So you can take this molecule right here and use hydroboration to get this. Notice here the OH is a wedge and the hydrogen is a dash. But they are the same molecule. So it makes it difficult to predict. If you are in a situation where you have a molecule like this, and you're trying to figure out what the alkene came from, what you can do is take that molecule and draw a conformation of it where the OH and the H are either both wedges or both dashes. So if I take this and say I rotate the bond on the left 180 degrees, that makes this OH a dash, and now that. Okay. Now this OH and this H are both dashes. They're on the same face as each other. Then what you do is you copy the line segment exactly as it's drawn. Then add in your double bond, and then add in your other groups around that double bond. And this is that molecule up there. Now, I am very, very good at drawing molecules in an unhelpful manner. What you'll need to do is work on taking a conformation that I've drawn and changing it into a conformation in a helpful manner. And that could be getting your H and the OHs syn to each other.